So next up, we have Professor Andrew Sabelhaus. He's with us already. Excellent. So he is an assistant professor in the Department of Mechanical Engineering and Division of Systems Engineering at BU, so Boston University, and the director of the Soft Robotics Control Lab. He does PhD in mechanical engineering at University of California at Berkeley and a postdoc at CMU. And the focus is on integrating embodied intelligence into soft materials with artificial intelligence. So again, a ton of distinctions, including a NASA Space Technology Research Fellow and the NSF Graduate Research Fellow back in the day. So thank you so much for joining us.
Yeah, many thanks, Professor Peterson. Can you all hear me?
Yes, you sound great.
Cool, wonderful, awesome. And I saw John Riefel posted a little shout out there to Tensegrity Research. Yeah, older stuff here on my shelf. And yeah, please excuse. Also, we are having sun in Boston today, Lake in Ithaca. What a wonderful gift. So hopefully my camera is still visible. Let me share my screen. Let's see, and hopefully the slides will play. Are the slides up?
They are up and they look great.
Okay, wonderful. I'm going to just briefly hide floating meeting controls and switch back. Okay, wonderful. So thank you all for having me today. I am really excited not just to be here as part of Embodied Intelligence 2023, but also to be in this particular session. I'm really excited to be, in a sense, kind of among other folks who are thinking about control systems and autonomy. I'm a control systems engineer, sort of joining the soft robotics conversation here. And what I'm hoping to bring to this today is a larger perspective on the question of what we would like to do when trying to integrate control and autonomy into soft robots. And I'll bring three different possible directions here based on the work that I was doing as a postdoc and with my new group at Boston University, thinking about robustness, scalability, and safety. So the higher level vision here is the conversation about integrating some amount of artificial intelligence with embodied intelligence. So please excuse the DARPA Robotics Challenge video. It's not here to illustrate the usual conversation about why we would need embodied intelligence, but more to contrast with oftentimes what we're looking at with the types of devices that we build that are softer, that have that sense of embodied intelligence. To illustrate this gap, right? Maybe why we would need to bring back in some of the artificial when we focused on the embodied. Oftentimes the motions of these devices, while very impressive with respect to the environmental interactions, are much simpler, right? You could imagine maybe if these rigid robots were successful, the types of motions they could perform are much richer. So there's a big gap here. And folks in recent years, very recent years, have been thinking a lot about how to bridge this gap. And oftentimes have been applying sort of traditional perspectives for traditional types of goals for what we might call controlling a soft robot, whether this is reinforcement learning or things like generating trajectories. We're thinking a lot about positioning of the robot's body in space. Oftentimes this comes with limitations with things like computation and implementing these in real time. And so the results are either limited to simulation only or pre-calculate a set of inputs, click go, and then let the embodied intelligence take over. So there's a question about whether or not that temporal separation of artificial and embodied is really going to be optimal for what we would need to bridge that earlier gap. And the times in which we have gone and been able to do real feedback, closed loop in real time for soft robot manipulators in particular, the environment has still been relatively simple, like well known, and matches our model pretty well, which there's a question of like, will that technique be transferable to the unstructured environments we're most interested in? And a big perspective here that I always like to think about with this conversation is a point that one of our colleagues made very eloquently just a few years back in a mathematical sense, with a goal of good tracking performance, right? Having a robot move into a particular pose, we end up reducing the compliance of the robot sort of by default. So there's a question of, if we were thinking about a traditional control goal, the tools that we have in our toolbox of having a system track a trajectory perfectly, the right solution in a sense is going to be something that's rigid. So if we're talking about systems that are no longer rigid, is that perfect tracking really going to be our goal? Right. So what does a control goal and a goal for autonomy look like that respects embodied intelligence, that brings it into hardware, that can happen in real time? And in particular, is there something beyond just positioning of a soft body in space? I think there are three possible options as part of this larger conversation. And I'm very interested in what you all are thinking about here too, especially other folks in control who are thinking about adapting our toolbox of techniques. So first one is robustness. This is something that Professor Mitre made an excellent justification for earlier, where we could think about if our models are imperfect, if we're simplifying our models, can we instead design controllers that accept that those models are imperfect and still have properties like maybe stability, something that we're comfortable talking about? Another one is to think about the scalability and real-time type of challenge. And if we were to reframe our problem that we might call a control problem, instead as a larger question of autonomy, we might be able to justify this like planning, something at a larger time scale, lower frequencies, that lets the embodied intelligence take over for short periods, in a sense. And the last one, I think, that really gets at the heart of our argument for soft systems is thinking about safety and interactions. We have a strong set of tools in control systems and in robotics that let us talk about things like safety verification, and they haven't yet been brought into soft robots. I'm going to show some really initial work in my group towards doing that for our particular types of designs that use these shape memory alloy wires as actuators. So this is a particular robot that I collaborated with back when I was at Carnegie Mellon with Zach Patterson, who's now a postdoc at MIT, where we had a shape memory alloy driven soft manipulator. And our approach with this was to think about robustness in the state space sense rather than robustness in the frequency domain sense here. Thinking about can we just express large amounts of the dynamics of the system as parametric uncertainties? And it turns out that this actually lets us do things like completely ignore gravity and put in a relatively arbitrary expression for damping and not worry about what the soft material is really doing, still get pretty good performance out. The other example here is thinking about planning. So if we have a robot that takes a relatively discrete set of actions in the first place, like this swimming frog-inspired robot that would push its legs in one direction, we could think about simulating a large number of options offline and then choosing between those actions. So instead, we've now discretized our problem by doing simulations beforehand. And an even simpler version is this underwater starfish robot that motivated the example with the robust control earlier, where it might even be the case that we could hand tune a set of these options and still get really impressive performance out. So thinking here about maybe put the computation offline, generating a smaller set of options for online. Transitioning to thinking about that question about safety and verification. So here's an example of a planar limb that has shape memory alloy wires on either side. Like Professor Mitra had said, for these types of actuators, they are controlled by temperature. So we're passing electrical current through them and they heat up, they contract, et cetera. So this is a test of a teach and repeat, a relatively representative traditional robotics problem. And so what we thought about for this particular issue was temperature safety for these shape memory alloy wires. It's actually a very common problem that other practitioners with thermal actuators will know and maybe if not love, at least respect the challenge of these things overheating and either losing the model properties, losing the model consistency, or just otherwise having a safety hazard. So a very simple method might be in terms of generating these trajectories. We could think about offline optimization methods, now just with extra constraints in our optimization problem. We did this and we showed that at least in this open loop sense, we could ensure some type of condition here. Now, that doesn't necessarily get us over the pre-calculate and click go problem, but it does lead a step towards this maybe intuition that what we're talking about here might be more about constraint satisfaction rather than tracking behavior. And here's where this really ends up coming in terms of loop closure. So we implemented a really simple feedback controller for this particular limb and showed that we can overheat it actually very, very easily. We could command an infeasible state, we could put in a disturbance, that kind of thing. And there's a tool called invariance that is highly used in things like legged robots. And the principle here is that if we can, under the action of our autonomy, our controller, render some set invariant, where the robot maybe never exits this set of states, we could call that safe. That's a very formal definition of this idea of safety. And luckily enough, for our shape memory alloy wires, the temperature dynamics, at least, not necessarily the stress and strain, the temperature dynamics, we could actually express them as a linear system and observe that they're monotonic. The intuition here is if you push more current through the wires, they heat up more. Less current means less temperature on the other side. And because linear systems have this very nice result for motion paths, motion planning from one position in space to another, we could go and say, what would be a maximum limit that would reach maybe our boundary, the boundary of our set that we're trying to render invariant? And we went and attempted this out for a number of different of these shape memory alloy wires. Oh, can you all hear me? Oh, I heard something. Is everything good?
All good. Yeah, no, sorry, not sure what that was, Andrew. We'll watch out for it.
Okay, no problem. Yeah, I just know these headphones are apt to cut out. So yeah, so the purpose of this one is that a very simple way to talk about invariance might be saturation or supervising the actions of another nominal control system. So here is an example of this infeasibility question here, where we ran the closed loop system, but then just included this saturation. And we showed that the robot indeed does not move in the motion that we originally intended, but still maintains some set of safety. So as opposed to thinking about tracking performance, we're thinking about constraint satisfaction here. You're looking at the blue lines versus the pink and the red lines in the plot that's evolving in the bottom right. And the last little bit of what I've started here at Boston University in particular with my group has been implementing these into practical robots. So this is a three-legged robot, still very much under review, trying to find its place out in the literature, but I think shows this nice example of how we could think about doing safety in a piece of hardware. So what we did was we took 5 of these individual limbs that move in 2 dimensions, connected them up just to have a simple example of what we might mean for something that's legged, and then went and performed a balancing action and had a really, really extreme disturbance come in here. So someone come in and really bend the robot into a way that the wires would have overheated. We showed that they don't, right? So a simple validation and verification here. That's actually all I have for you all today. My hope is that this brings some maybe a little bit of lightness into our conversation for control engineers. I guess the only last thing to say about that is I am very much looking forward to collaborations on this. I know that all of these are really cutting edge topics. So please let me know if you're also interested in things like safety and verification from an artificial intelligence sense. And let me bring back my meeting controls and I will stop sharing.